Look at almost any device around you right now that does something clever. You know, your phone, your laptop, maybe the microwave in your kitchen.
Right, or even just like the card reader at the local coffee shop.
Exactly. They all serve completely different purposes, built with totally different designs.
But at the heart of every single one of them is the exact same quiet miracle.
A tiny sliver of silicon etched with just unimaginably small patterns. Welcome to this deep dive.
Thanks for having me.
Today, our mission is to completely demystify what is fairly called the silicon age. And we're going to do this by slowing right down, really unpacking the fundamental building block of the modern world.
And we're assuming you, the listener, have absolutely zero prior science background.
Right, none at all. But by the end of our time together, you will understand exactly how something as basic as, well, refined sand ended up running basically everything.
It's crazy when you think about it. Silicon is a genuinely strange substance. I mean, the story of how humanity learned to exploit its specific quirks it's literally the story of how our modern civilization was built.
Okay, so to wrap our heads around silicon, I guess we first have to start with how different materials in the physical world handle electricity.
Yeah, that's the best starting point. Materials generally fall into two very distinct camps when they're dealing with electrical current.
Okay.
On one side, you have your conductors. Copper is the classic example here, along with, most metals.
Right, because their atomic structure allows electric current to just flow through them with virtually zero resistance.
Exactly. The wires in the walls of your house are copper for that exact reason. They move power from the grid to your outlets totally effortlessly.
Effortlessly, right. And then what's on the other side?
Well, on the opposite end of the spectrum, you have insulators. Materials like rubber, glass, plastic.
Stuff that blocks electricity.
Yes. Their atomic structure tightly binds electrons, so it completely blocks electric current from flowing.
Which is why those copper wires in your walls are wrapped in a plastic coating.
Right, so the electricity stays in the wire and doesn't just, leak out into the wooden frame of your house and burn it down.
Right. Okay, let's unpack this. We have conductors that let electricity flow and insulators that stop it cold. But today's deep dive is entirely focused on a semiconductor.
Yeah. A semiconductor sits right in the middle between those two extremes. It conducts electricity, but it does a remarkably poor job of it.
See, on the surface, that sounds totally useless.
It does, right?
It's like hiring an employee who is deliberately mediocre at their one specific job. I mean, if we want electricity to flow through a device, why bother with a material that can't decide what it wants to be?
That's a totally fair question.
Why not just use copper?
Because that indecisive nature is actually the entire point. What makes a semiconductor so incredibly valuable is that its willingness to conduct electricity can be externally controlled.
Oh, interesting.
Right. With a copper wire, it's always conductive. You can't just tell copper to suddenly stop acting like copper.
It's just always on.
Exactly. But a semiconductor is sitting on the fence. We can push it one way or the other. And being able to turn a material's conductivity on and off incredibly fast is the foundational requirement for building a switch.
A switch. Which brings us back to silicon, I guess, the most famous semiconductor on Earth.
Yep, silicon. It is wonderfully abundant, mostly because it's, well, the main ingredient in ordinary sand.
But wait, we can't just scoop up sand from the beach and stick it in a motherboard, right?
Oh, definitely not. Raw silicon, even after it has been completely purified into a pristine, flawless crystal lattice, is basically just a weak insulator.
So it doesn't really do much on its own?
No, not at all. The real magic requires a laboratory process called doping.
Doping, like adding performance enhancers.
Kind of. It involves deliberately introducing tiny amounts of other elements into that otherwise pure silicon structure. And we are talking about adding maybe a few atoms of an impurity for every million or even billion atoms of silicon.
Wait, really? So we spend immense effort purifying sand, getting it flawlessly clean, just to intentionally contaminate it.
Yeah, that's exactly what we do.
That's like adding a single microscopic drop of food coloring to an Olympic swimming pool.
That is a perfect analogy. And depending on the specific element you use to contaminate the silicon, you fundamentally alter its electrical personality.
How so?
Well, if you add an element like phosphorus, for instance, you create what we call N-type silicon.
Okay.
N-type. The N stands for negative. That's because phosphorus introduces a slight surplus of free-floating electrons into the material. And since electrons carry a negative charge, they are super eager to just move around.
Okay, that makes sense. Extra electrons equal a negative charge.
Right. But if you dope the silicon with an element like boron, you create p-type silicon.
And the P stands for positive.
You guessed it. Boron actually creates a deficit in the silicon lattice. It literally creates empty spaces, we call them holes, where an electron ought to be, but just isn't.
Oh, okay.
And in the physics of semiconductors, those empty holes actually act as positive charges.
Wait, you lost me there. If a hole is literally just the absence of an electron, how can empty space have a positive charge? I mean, it's literally nothing.
Yeah, that is a really great distinction to make. It's not the empty space itself that carries the charge. Think about the silicon atoms surrounding that hole.
Okay.
They still have their full complement of positively charged protons sitting in their nuclei.
Right.
Normally, those protons are perfectly balanced by negatively charged electrons in orbit. But because doping created a missing electron, that local area of the atom now has more positive protons than negative electrons.
I see.
So the net charge becomes positive. The hole is just, the easiest way to visualize that positive vacancy moving around as electrons jump in and out of it.
I totally get it now. The underlying structure provides the positive charge because the balancing electron is missing. So we have N-type silicon packed with extra wandering electrons and P-type silicon packed with positive vacancy.
Exactly. But sitting on a desk separately, neither chunk does anything particularly useful.
Okay, so when does it become useful?
The revolution happens when you bond a piece of N-type silicon directly against a piece of P-type silicon.
Oh, wow. What happens at the border where they touch?
Imagine the N-type silicon as this crowded parking lot with too many cars frantically driving around.
Sounds stressful.
It is. And the P-type silicon is an adjacent parking lot with plenty of empty parking spaces. The moment you push these two lots together, the extra cars, the electrons, immediately rush across the border to fill the empty spaces on the other side.
Huh. But wait, wouldn't that seem like it would just neutralize the whole thing?
It neutralizes the border area, yeah. By rushing across, those electrons lock themselves into the holes right at the junction.
Okay.
And they create this localized gridlock, a dead zone we call the depletion region. Because all the free electrons are now stuck in holes, there are just no loose charge carriers left in that middle border.
Wow. Okay.
And that gridlock zone acts as a physical wall, completely blocking any further electrical current from flowing across the silicon.
So by just putting them together, they instantly create an internal traffic jam that stops electricity?
Exactly. But we can break that traffic jam.
How do you do that?
If we hook a battery up to this piece of silicon and apply voltage in a specific direction, the electrical pressure actually forces the gridlocked electrons out of their holes.
Oh, so it just blows through the wall.
Yep. It instantly collapses that wall and allows current to flow freely. But if we flip the battery around and reverse it, the pressure actually widens the gridlock, making the wall even thicker.
Wait, so you've basically just created a one-way valve for electricity and with absolutely zero moving parts.
That's exactly it.
Current can push through the gridlock in one direction but gets completely blocked in the other.
Right. And that PN junction, that tiny one-way valve, is honestly the seed of the entire digital age.
That is wild.
But a valve that just permanently sits there blocking traffic in one direction isn't very smart. The real leap forward happened when engineers figured out how to actively control that junction.
How did they do that?
They added the third connection, and that created the transistor.
Okay, the transistor. How does that third connection change the game?
Well, a standard transistor basically sandwiches three pieces of doped silicon together. Think of it like a pipe with a mechanical gate right in the middle.
Okay, I'm picturing it.
The main electrical current really wants to flow from one side to the other, but the depletion regions, that gridlock we talked about, block it.
Right, the wall is up.
Exactly. The third connection acts as a control knob. When you apply just a tiny electrical voltage to that third connection, it alters the electrical field inside the silicon, temporarily dissolving the gridlock.
So you apply a little control voltage, the gridlock vanishes, and the main current just rushes through. The switch is on in.
Bingo. And the millisecond you remove that tiny control voltage, the gridlock instantly reestablishes itself.
And the main current is blocked again. The switch is OFF.
Exactly. And because this entire process is just electrons shifting positions within a solid crystal, there's no physical switch flipping up and down.
Right. There are absolutely zero moving parts to wear out or create friction.
None at all. A modern transistor can flip between on and off for billions of times every single second.
Billions of times. It's as hard to even fathom. And that brings us to how we get from physics to software, right?
Right.
Because most of you listening probably know that computers use binary. Software is written in ones and zeros. But there is a massive conceptual gap between a physical silicon switch and, like, a program running on a screen. How do we cross that bridge?
Yeah, so that bridge is constructed by wiring these transistors together into specific patterns. We call them logic gates.
Logic gates.
Right. Imagine you have a wire carrying electricity, and you place two transistors sequentially along that same wire.
Like two toll booths on a single lane of highway.
That is a great way to picture it. For the electricity to make it to the end of the wire, you have to apply a control voltage to the first transistor to open it. And you have to apply a control voltage to the second transistor to open it.
So if either one is closed, the current just stops.
Right. And you have just physically built an A&D gate.
Oh, wow. So if I wanted an OR gate, I would, like, split the wire into two parallel tracks, put a transistor on each track, and then merge them back together.
You've got it perfectly. In that arrangement, current reaches the end if you open the first transistor or the second transistor.
That is amazing.
By arranging the physical tracks and switches, you are literally hard-coding logical rules into the silicon.
So when you string thousands or, I guess, millions of these A&D OR and NOT gates together,
You create circuits that can add numbers, store information in memory, and execute really complex sets of instructions.
so every pixel on a screen, every saved password, every artificial intelligence calculation, it's all just an unimaginably vast arrangement of those microscopic logic gates, routing electrical traffic based on the rules we built.
Exactly. The entire edifice of digital technology rests on the controllable conductivity of that doped silicon junction.
But, I mean, making one switch or a handful of logic gates isn't enough to build a pocket calculator, let alone a smartphone.
No, definitely not. Early computers used really bulky individual switches, whether they were fragile glass vacuum tubes or early hand-wired transistors.
Right, and they took up entire rooms just to do basic math.
Exactly. The only way forward was to scale up.
Okay, so how did they do that?
Well, engineers realized they couldn't keep soldering physical wires between individual components. It was just too slow and too big. They needed to put all the transistors and all the microscopic wiring connecting them onto a single flat wafer of silicon.
Oh, and this was the birth of the integrated circuit, or the microchip.
Yep. And this marks the beginning of Moore's Law, too.
Right, the famous observation by Gordon Moore that the number of transistors we could fit onto a silicon chip was roughly doubling every 2 years.
Exactly. That compounding growth was driven by this totally relentless campaign to shrink the manufacturing blueprint. Today, a modern microchip the size of your fingernail holds tens of billions of individual transistors.
Okay, let's focus on that for a moment because the scale is just baffling. How do you actually mass produce something that small?
It's extremely difficult.
I mean, a single transistor today is far smaller than a speck of dust. You can't use tiny mechanical tools to carve something measured in atoms.
No, you can't. You have to use light.
Light.
Yeah. The process is called photolithography, and it is effectively atomic photography.
Okay, walk me through that.
Sure. You take your pure silicon wafer, dope it to create your P-type or N-type foundation, and then you coat it in a light-sensitive chemical called a photoresist.
Ah, so it really is like preparing photographic film.
Precisely like film.
Yeah.
You then take a photomask, which is basically a physical stencil of the incredibly complex microscopic city you want to build.
Okay.
You shine a specific type of light through that stencil and project the pattern down onto the silicon wafer.
I see.
The light passes through the gaps in the stencil and hits the photoresist chemical, altering its structure. Then you wash the wafer in a chemical bath, which dissolves the altered areas.
Leaving your microscopic pattern perfectly transferred onto the silicon.
Exactly. So you aren't carving the silicon directly at all. You are projecting a map of light onto it and using chemicals to eat away the specific patterns.
Right, and you repeat that process dozens of times, layer by layer. That's how you build up the complex 3D structures of billions of transistors and the incredibly intricate copper wiring that connects them all together.
Okay, but wait. If we are shrinking these transistors every 2 years, eventually the features become smaller than the wavelength of visible light itself, right?
Yes, that was a huge problem.
Because the stencil wouldn't cast a sharp shadow anymore. The light would just like bleed around the edges.
Exactly. And that physical limitation forced the industry to develop extreme ultraviolet lithography, or EUV.
Mm.
We basically had to abandon visible light entirely.
Wow.
EUV light has an incredibly short wavelength, which allows for microscopic sharpness. But it presents a massive engineering nightmare.
Why is that?
Because EUV light is absorbed by absolutely everything. It is absorbed by glass lenses, and it is even absorbed by the air itself.
Wait, what? How do you focus a beam of light if you can't use glass lenses and it gets absorbed by the air?
You have to build the entire machine inside a high vacuum chamber, completely removing all the air.
That sounds insanely expensive.
Oh, it is. And instead of lenses, you use the flattest, most highly polished mirrors humanity has ever created. These mirrors basically bounce the EUV light back and forth, focusing it through the stencil onto the silicon.
That is incredible.
To give you an idea of how flat they are, if you scaled one of these mirrors up to the size of an entire country, the tallest bump on its surface would be less than a millimeter high.
Oh my God. Well, this totally explains why the physical manufacturing environment is so fiercely protected.
Yeah, it has to be.
I mean, if you are using extreme ultraviolet light to put wires that are only a few dozen atoms wide, the slightest contamination is disastrous.
Disastrous is the right word. The factories that house these machines, they're called fabs, have to be significantly cleaner than a hospital operating theater. If a single microscopic stray particle of dust, or even just a flake of dead skin from a worker, floats through the air and lands on the silicon wafer during the printing process.
It acts like a boulder on a highway.
Yes. It casts a shadow during the lithography step, preventing the light from hitting the photoresist.
And that shadow basically breaks the microscopic wire you were trying to print.
Exactly. And because billions of transistors are sequentially wired together in these complex logic gates, breaking one critical wire can ruin the entire chip.
You know, this really clarifies a geopolitical puzzle for me.
So?
Well, we frequently hear about global chip shortages disrupting everything from car manufacturing to national defense. And I always wondered, if the main ingredient is just silicon derived from sand, why is there a bottleneck? Why can't any country just build factory and print their own chips?
Because the bottleneck isn't the sand. It is the sheer mind-bending complexity of the tools required.
The machines themselves.
Right. Creating an EUV lithography machine requires coordinating hundreds of thousands of specialized parts. For instance, you need lasers that shoot microscopic drops of molten 10,000s of times a second just to generate the EUV light in the first place.
That is, I can't even wrap my head around that. So you might have access to all the silicon in the world, but you don't have the multi-billion-dollar oven necessary to bake it.
Exactly. The know-how, the supply chains, and the machines capable of doing atomic-level photolithography are concentrated in a very small number of companies and regions.
Which makes it hugely political.
Absolutely. The entire modern economy relies completely on these tiny switches, yet very few places on Earth can actually mass-produce the most advanced versions. Whoever controls the manufacturing of these switches effectively controls the future of global technology.
And looking toward that future, we are facing an entirely different kind of bottleneck, aren't we? A physical one.
Yes, we really are.
Because we have spent 60 years relentlessly shrinking these transistors to maintain Moore's law. But you can't carve half an atom. The blueprint has to stop shrinking eventually.
Physical reality is aggressively catching up with our engineering ambitions. The components of a modern transistor are now so incredibly thin that they are measured in mere handfuls of atoms.
Wow.
And when you get down to the atomic scale, the reliable rules of classical physics begin to break down, and the strange rules of quantum mechanics take over.
Wait, how does quantum mechanics interfere with a switch?
Well, remember the depletion region?
The gridlocked wall of electrons that stops the current when the switch is off?
Right. We rely on that wall being absolutely impenetrable. But at the atomic scale, a phenomenon called quantum tunneling occurs.
Quantum tunneling?
Yeah. The wall of the transistor is now so physically thin that electrons sometimes just teleport right through it.
Teleport.
Literally. They just appear on the other side.
But if the electrons can bypass the wall, the switch isn't really O-off-F anymore. Current is just leaking through.
Exactly. The switch becomes leaky and completely unreliable. And if you can't trust your switches to definitively stay OFF, your logic gates break down and your software just stops working.
That sounds like a massive problem. We are literally running out of atoms to build reliable physical walls.
We really are.
So does this mean the party is over? Will our devices eventually just hit a permanent performance ceiling?
Not necessarily.
Yeah.
It represents a maturation of the technology, not necessarily an end to progress.
Okay, so how do we get around it?
We just can't rely on simply shrinking the flat two-dimensional blueprint anymore.
Mm-hmm.
Engineers are adapting by fundamentally changing the architecture.
In what way?
Instead of laying transistors out in a flat urban sprawl, they are building vertically. They are stacking chip layers in 3 dimensions to pack way more processing power into the exact same footprint.
Oh, that makes sense.
And they are designing highly specialized logic gates tailored for specific tasks, like artificial intelligence, rather than just relying on general-purpose chips. Plus, they are actively researching new, exotic semiconductor materials to eventually replace silicon altogether.
So the path forward is forcing us to be much more creative than just, shrinking the stencil.
Exactly.
Wow. Let's trace this incredible journey one last time. We started with ordinary sand. From that sand, we extracted silicon, a completely mediocre material that naturally conducts electricity very poorly.
Right, and then we perfectly contaminate that silicon through doping, introducing deliberate flaws to create N-type regions with extra electrons and P-type regions with empty holes.
And when we push them together, those electrons and holes crash into each other, creating a gridlock depletion region, a one-way valve for electricity.
Yep. Then we add a third connection to that valve, giving us a way to selectively clear the gridlock using a control voltage. That is the transistor, a switch with 0 moving parts.
Then we arrange those tiny physical switches into overlapping patterns on a single wire, creating logic gates that force electricity to do math.
And finally, we scale it up. Using extreme ultraviolet light and flawlessly flat mirrors inside pristine vacuum chambers, we project microscopic stencils to carve tens of billions of these logic gates onto a sliver of silicon the size of your fingernail.
It's honestly breathtaking. That chain of physical manipulation is what built the digital world we inhabit today.
It really is.
So the next time you casually reach into your pocket, unlock your phone, and check a message, spare a thought for the invisible metropolis in the palm of your hand.
Yeah, tens of billions of microscopic switches carved into purified sand are flipping on and off billions of times a second in perfect lightning-fast coordination just to display that one notification.
Unbelievable.
But it leaves us with something quite profound to consider for the decades ahead.
What's that?
Well, for over half a century, the entire structure of our digital reality has been built on exploiting the highly predictable classical properties of silicon atoms.
Right.
But as we shrink our ambitions down to their absolute physical limits, we're entering a space where those classical rules just dissolve.
Yeah.
If our future requires us to build devices that rely on the strange, teleporting reality of quantum physics,
Yeah.
how fundamentally will our technology and our relationship with it have to shift to accommodate that new frontier?
Man, that is the boundary we are approaching next. Something to really mull over. Thank you for joining us on this deep dive into the Silicon Age. Keep wondering, keep exploring, and we'll see you next time.